because it has a wider angle, but this will do. Okay, so question was I was going to ask, by raising hand, can any remember, it was back actually in Unit 4, but what electronegativity is? Anyone by raising hand somewhat remember? What do you remember, McKay?
Isn't electronegativity the willingness to give up electrons, basically?
Ooh, close. Have a smiley face trying. It deals with electrons, but there's a different part to it.
Which atom in a molecule has like a stronger pull of the valence electron?
Good. So we're not actually giving them up, but it's a tug of war of them. Have a smiley face for that, Jeff. So when two atoms are bonded, hydrogen to chlorine, we've been drawing them like this, right? Okay. This line represents what? Shared electrons. But when you have an atom that has a higher electronegativity, it doesn't share equally with the other atom. So the trend for electronegativity, in case you forgot, is this is the lowest electronegativity, that corner is the highest electronegativity. So chlorine and hydrogen, chlorine, the way I think about it is it's a tug of war, and chlorine is going to win. So underneath this picture for me, draw an arrow. So chlorine is winning the tug of war because it has a higher electronegativity. And because of this, we result in an interesting property of polarity. What is the charge of electrons? Negative. So if chlorine pulls the electrons more towards itself, chlorine becomes slightly negatively charged. Okay, so we get a partial negative on this side of the molecule. Now the reason why I use the word partial is because it's still being shared. Chlorine didn't rip the electrons off of hydrogen, but it is pulling them away. Now, if hydrogen is losing electrons, what charge is it going to become? Positive, right? And once again, it's just a partial. So to show that positive charge, on the end of this arrow, we make it a plus sign. So these arrows show that charge. They show, hey, this side is positive, and this side is negative. This arrow right here is known as a dipole moment or movement. So it's called a dipole arrow. The word dipole meaning, what does di mean? Two. Pole because of positive, negative poles, right? Think of like north and south pole. That's what a polar molecule is. Once again, that's why we use the word polar. A polar molecule is when you have an unequal distribution of electrons, and so your molecule literally turns into a little magnet. That's the way I think of polarity, is it turns a molecule into a magnet with a negative and positive side. Yeah, Belle?
Water is polar, right?
Yes. Yeah, so water, and that's one of the key ones we'll talk about next time, and your lab dealt a lot with, was the idea of how water is polar. So here's the idea, right? So for something to be polar, it's because you have unequal electronegativities, and the electrons get pulled to one side more than the other. Okay, so imagine it like a tug of war going on here. So our first objective here is to determine, looking at a molecule, to say if that molecule is polar or if it's nonpolar. So the two things we look at, or the main thing really, is all about symmetry. If the dipoles are symmetric, they cancel each other out. So for example, in this shape right here, draw some arrows with me. So let's say B, oh, that one is not. What? So B is pulling in all directions on A. But since the shape is symmetrical, right, you could visualize it kind of like a 3D tug of war, not 3D, but three-direction tug of war. Does A actually go anywhere if they're all the same pole? No. So this molecule would be classified as nonpolar because the tug of war gets canceled out. Versus if you have a shape like this one, this shape is not 3D symmetrical. Now when we say 3D symmetrical, you can think kind of like the kindergarten idea of like, if you can cut it in half, and it's the same on both sides, it's symmetrical, right? But you gotta think in like X and Y axis here, because if I cut it this way, is it symmetrical?
Yeah.
But if I cut it this way, it's not. And so this is classified as a polar molecule. So symmetrical means nonpolar, asymmetrical means polar. Now, 2 checklists, once again, to determine if something is polar. Okay? If it's asymmetrical, it's going to be polar. Now, one of the key things that makes it asymmetrical are the lone pairs or the ghost. If an central atom has a set of lone pairs, it's always going to make it asymmetrical because those lone pairs always are bending the angles away. So that's kind of the one key thing you'll look for. That says shape, by the way, if you can't tell. It's hard sometimes and it falls right on that line. The second thing you look for is asymmetric atoms. What this means is something like this, where here's your center, 3 of the sides are chlorine, but 1 of the sides is hydrogen. That's classified as asymmetric, because one side's hydrogen, the others are chlorine. That would still be asymmetric, technically, if one of these was an H. Even though you have 2 H's and 2 Cl's, they're not symmetric straight across from each other, so it's still a polar molecule. Any general questions on what polarity is? Okay, flip your notes back to this table, the big Vesper table that we did where it has like AB2, AB3, and let's fill in that polar and nonpolar column, okay? Okay, so once again, these are the 2 things you're looking for to see if something is polar. So I'm going to make a little checklist here. So you check to see, does it have lone pairs on the middle? Okay. Second thing you check for, is it bonded to asymmetric, which pretty much means different atoms. If one of these 2 things is true, then it will be polar. Okay? All right, so our first example, AB2, I didn't write down what we did. Was it CO2? Was that the example molecule I gave you? Okay, so I'm just going to draw that so we can talk about it up here. You should already have that in there. So, are there lone pairs on the middle? Nope. Bonded to different atoms, oxygen, oxygen, nope. So this would be classified as non-polar because it doesn't meet either of those requirements. It's completely balanced. Okay? AB3 is our next example. Was it SEO3? Thank you. This is the shape that you should have. So to determine it's polar, first check, are there lone pairs on the middle? Nope. Bonded to different atoms, oxygen, 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 nope. So it's non-polar, perfectly balanced. Stop me if you have a question. Okay, AB2E. What did we do for this example? Oh, that's right. Thank you. All right, so here's my structure. Lone pairs on the middle. Yep, that's what these are. So lone pairs are dots on the middle atom. So because those are there, this would be classified as a polar molecule. Because what do those dots do to the shape? Not so much pull, you're doing the right motion, Seth, but they push even, right? So they make it not symmetrical because it's not really a straight line anymore, right? It's going to be bent. So that's why they affect the polarity. Okay, I'm going to come over here. Let's see, AB4. Was this the one that we did? Okay. Pretty sure I did the same examples for all my periods, but I kind of just made them up as we went. So, okay. For a smiley face, don't say it out loud. What sign should we do? Give me a thumbs up if you think it's polar, thumbs down if you think it's non-polar. Keep it like close to your body though so other people can't see. So is this shape polar or non-polar? This means polar, this means non-polar. All right, if you're saying non-polar, have a smiley face. Why is it non-polar? Yeah, perfectly symmetrical, right? Doesn't have lone pairs. All of them are H's. Balance means not polar. So one of the biggest things is don't flip the definition. Otherwise, you'll get them all backwards on the quiz. Okay, so polar, I think of the word poline. A polar molecule is poline because it's not balanced. Okay? All right, next example, AB3E. What's our one on there? NH3. Okay, let's earn another smiley face here. Thumbs up polar, thumbs down non-polar. Show me what you think. Show me a vote one way or another because then I can know if we're understanding or if I need to help you. Oh, very good. Why is it polar?
Because the two above.
These little guys, right? Push those bond angles away and make it not equal. So this would be polar. Okay, one more example. AB2E2. And we did water, right? Okay, thumbs up polar, thumbs down non-polar. This one is polar. So what about this makes it polar?
The two pairs.
Yeah. So this is a perfect example where you got to separate what we draw to what it does. Is this actually a straight molecule like it's drawn here? What do these two lone pairs do? They bend it, right? And because it's bent, that's what makes it polar.
But if they're both pushing, then when does it bend?
So if you think of like, when you have four domains, right? What's the shape if you have four domains?
Tetrahedron.
Good, right? So the shape for four domains is not a shape like this, right? It's the 3D shape. And so even when you have two lone pairs, you need to get like here, let me get I think I have a model set here. Nope, I borrowed it to someone. Here's your tetrahedral, right? If a lone pair's here and a lone pair's here, they're not actually straight across from each other like it looks on here. Does that make sense, Keeson? But great question, because that's a very common misconception is lone pairs canceling each other out. But the idea is they get farther away by doing the tetrahedral shape, but then it makes it so it's not linear. So, other questions on polar or non-polar? Yeah, Tyler.
If it's linear, can it be polar?
Yes, it could be.
Not like,
Do you know what would make it polar?
I'm sure it's
Well, linear will actually never have dots on the middle, but
Different atoms.
if this was sulfur, that makes it polar. So this situation is what asymmetric means. So, great observation. So, any other questions on that?
What if it's like HBr for each two of them?
Okay, pull out your homework assignment, everybody, and we'll look at that one together, Logan. So, pull out your homework assignment from last time. Question, Jeff?
So with the thing of like the oxygen carbon sulfur thing,
Yeah.
with that, so is the oxygen kind of getting closer to the carbon because of the sulfur? Like, what makes it like polar, even though technically it can't go, oxygen can't go anywhere?
So, it's not so much that the atoms are going anywhere, it's where the electrons are being pulled. And they're not being pulled equal because oxygen pulls harder than sulfur does. And so if you're having a tug of war here, more electrons would be pulled this way than that way. And so there's your magnet, right? A negative and a positive side. If you can't designate a negative and positive side, it's not polar. All polar molecules will have a negative side and a positive side to them. Does that make sense? Okay. Okay, so on your homework, Logan asked about the first one, right? Is that the one you're asking?
Yeah.
So the ones that have just two are kind of an interesting situation. So really, when there's only two things bonded, go back to the definition of what it means for something to be polar. So what does it mean if something is polar? Yeah, it has one side that's negative and one side that's positive because it's not an equal tug of war. So if you only have two things, is this an equal tug of war? Nope, because one side's BR and one side is H, and BR is buffer than H is. So this would be polar. Okay? Yeah, Haley.
So were all the ones with two polars?
What if it's that? Why? So the only time it can be non-polar with two is if it's identical, because then it's like having a tug of war with yourself. So, any other general questions? Action. Okay. An intermolecular force is a force that exists between two different molecules. Okay? So for example, let's look at water. So water feels a force of attraction to other waters. We often represent intermolecular forces by dashed lines. Dashed or like dotted. Because it's not a true bond. Like this one. But it is a force of attraction that does exist. Now, I would bet that a lot of you have experienced the pain of intermolecular forces if you have ever belly flopped into a swimming pool, or back flopped, or side flopped, or face flopped, or whatever, right? Face flop's probably the worst, right? Got a bloody nose one time from doing that, right? The way I visualize it is when you belly flop, and it literally will make that sound, right, if you do a good one. It's because those little water molecules are playing Red Rover against you. They are linked together through this intermolecular force. And so if you don't break the force by jumping straight, then you feel it instead. Now notice, I can break that force once you go into the water, right? When you go into the water, you're literally moving the molecules apart from each other. I'm not breaking that force. Does anyone know what it takes to break a true bond of water? A lot more than just jumping into a pool. Electricity. If you send electricity through water, you can actually get it to separate. So first off, with intermolecular forces, you need to separate. They are not a real bond. But they still result in actually a lot of properties that we see, and that's what our lab last time was all about. So today and then in connection next time, we'll bring that lab back up and explain all those things you saw based on intermolecular forces. The opposite, by the way, in case like you're curious, so the true bonds are called intramolecular forces because they're within a molecule versus inter, which is between. okay? So they're much weaker than real bonds, but they're still there and they still cause things to happen. Right, so once again, make sure you emphasize this is the force we're talking about, the between force. One of the things that it causes is things to come together. If we didn't have intermolecular forces, everything would exist as a gas. The reason why something goes from a gas to a liquid or to a solid is because the magnets of the molecules start pulling them together. But if there's no magnetism between them, they would just stay as a gas their entire life. Which, for example, why it's so hard to make helium not a gas. Don't quote me on this, but I'm pretty sure to turn helium into a liquid, so to make liquid helium, you have to be at what is called 4 Kelvin, which is like you can't obtain that on Earth. Like, it has to be done in a lab or like in outer space and stuff. Because helium has no force of attraction to itself. So it would rather just be a gas. Things that are solid have a very strong attraction to themselves, which is why they feel solid to us. Jeff, did you have a question?
Yeah, I was just, how come with water, the tension's only like, there's only surface tension, but like once you're in it, it's fine?
So there's still tension within water, actually. That's actually how you swim. It's like a weird way if you've never thought about swimming, but literally like to swim, you're grabbing molecules with your hand and pushing them behind you. And that's what propels you forward. If you couldn't grab those water and push them behind you, you couldn't swim. We would drown. Because there'd be nothing to like move you through the water. So there still is forces, but it's kind of that idea of where it's not super strong, so as you're moving around, you're breaking it at the same time. Does that make sense? A little bit. So, and we'll talk more about surface tension next time as well, too. Yeah, Addie.
So like when you're swimming, like you said you break them, but when you like move past a certain point, do they just like breathe?
Yep. Yeah, because they're just magnets, right? So it's like you push the magnets apart, but then if there's nothing between them, whoop, they'll link back together. Another kind of cool example, have any of you guys ever been up to Park City and like the summertime and you can watch the ski jumpers like do tricks into the swimming pool? If you've never gone, it's really cool. I don't know when they do it or how often they do it, but it's really cool. So for those that have seen it, they do something to the water though when the ski jumpers are going. Yeah, so they send massive jets in the water because it breaks up the Red Rover game. What that does is that if the ski jumper messes up their trick and they land the wrong way, it doesn't hurt. They could do whatever trick they want. You could belly flop into it and it wouldn't hurt. Because in a sense, there's no tension because they send the bubble. It's kind of the same idea of like doing a foam pit, right? That's why people practice tricks into a foam pit, is because it's safer than like on a solid ground, right? Yeah.
Is it kind of like breaking like the surface tension? Because I've heard people go like cliff jumping, like if it's kind of high, they like throw a rock to like.
Exactly. Yep. Same idea. Is if you can break the surface tension, then it takes away that force that you feel. Exactly. I mean, that's on the other side why cliff jumping from certain heights, like at Lake Powell, is like illegal. Is not because they're like trying to ruin your fun. It's because you could literally die from certain heights because it's so hard. Like water can be almost like concrete if you hit it the wrong way. So, yeah, great connection. Okay, so now we have 3 types of forces. So this force of attraction we've talked about. Now we have 3 classifications. So the first one is known as a dipole-dipole interaction or a dipole-dipole force. Okay? Now all the forces, think of magnets. That's the best way to visualize these because that's what they are. And you're familiar with how magnets work. Okay? A dipole-dipole force is when you have one molecule that is polar. So this molecule right here is polar because this side's negative and this side's positive. And that's what polar means.
What's that sign mean again?
This is a sign for partial. Yeah, so it's saying partially negative and partially positive. Good question, Belle. It can feel an attraction to another polar molecule because it's also positive and negative. So anything that is polar experiences this dipole-dipole force. So the negative end of one gets attracted to the positive end of the other. Once again, keep in mind, this is the force we're talking about, the force between. Second type of force that we have is known as a London dispersion force. Okay? Now, first off, recognize this keyword here, temporary. Okay? A London dispersion is a temporary magnet. Being that it's only temporary, would you say it's stronger or weaker than the dipole force? It's weaker, right? Because it's not a permanent magnet. Dipoles are permanent magnets. London are temporary magnets. The way this temporary magnet works is the idea of the electrons. Often when we make models, right, like these guys, or draw pictures, we show the electrons as evenly distributed. But electrons are not stationary things. So if we were to play a game, it'd probably be kind of dangerous, but if we were all to stand up, and I just said, okay, run around the room, and you all just started running around the room, okay? And then I said, freeze. Could there be a chance when I yell freeze that all of you are on one side of the room?
Yes.
Right, that's possible. And if you're electrons, so look at our picture here, we get a temporary magnet because negative on one side, positive on the other. But it's only temporary. Why? They're always moving, so it's not like they freeze, they can easily shift back. You can, though, cause a domino effect with other molecules. So if we're all electrons, and pretend the students on the other side of the wall are electrons, if we all run that way, it would make them do the same thing, right? So that's the London to London force, is when you have one shift and another shift, and so then they get attracted to each other. But being that there's nothing holding those electrons there, it's pretty weak because they can just shift back. It's not a permanent magnet that stays. All right, last type of force, we have dipole-dipole, we have London, and then we have what is known as hydrogen bonding. Once again, notice the comparison. This is an extreme magnet. So we have dipole, which is a magnet. London is a temporary magnet. Hydrogen bonding is the extreme magnet, so it's the strongest of all the forces. The way that this extreme magnet works is there's two requirements. First off, you have to have a substance that is very, very electronegative. And there's only 3 that scientists have found and measured that make it this extreme. So the 3 elements are nitrogen, oxygen, or fluorine. So I'll often refer to NOF when we talk about hydrogen bonding. Yeah. So it's interesting because chlorine's like on that, it's close to that area, but because it's down a row and bigger in size, it isn't as strong. It still pulls, right? It still causes dipole, but it doesn't fall into the category of hydrogen bonding. But good one to look at because a lot of times it's like right there too. So we have to have one of those 3. The other requirement is the hydrogen, hence the name hydrogen bonding. Everyone look at your periodic table. Look at your periodic table, or the one up there. Find hydrogen. How many electrons does hydrogen have?
1.
Only 1. So if oxygen is pulling electrons away, and hydrogen only has 1 anyways, what gets left behind if you take away its only electron? Just the nucleus, right? Literally, we're pulling the only thing on the shells that it has. So hydrogen not only becomes positive, but it becomes super positive.
Wow.
Because you just have this bare nucleus with no electrons around it. Okay? So the same thing's going to happen here, we are super positive. And so this force, this is the hydrogen bond. That's why it's an extreme magnet, is because that positive is really positive and this negative is really negative. So it's like a dipole, but it's an extreme one because of hydrogen. Okay, so once again, the requirements are hydrogen is losing its only electron, giving it a very, very positive charge left behind. Now, the requirement is for this force to happen, the hydrogen has to be directly bonded to one of those three, N, O, or F. If you don't have a true bond here, it can't do the tug and pull the electron away. So the way we often talk about in my AP chemistry class with hydrogen bonding is look for a Knopf sandwich. Okay? You need N, O, or F, and then H on both sides. The true bonded side to form the hydrogen bond side. Questions on that force for now? Okay. Is there another one? Oh, last thing, but it's not a real bond. It's kind of the catch. Scientists called it a hydrogen bond, probably because it is strong, but it's not as strong as the real bond. Okay? This is a real bond. That's a hydrogen bond. Okay, flip the page over, and what we're going to do is we're going to summarize all three forces and then practice identifying. And then that's the last thing we'll do today. Okay, so dipole-dipole is the charge of attraction between permanent dipoles. In order for something to have this force, it has to be polar. Or vice versa, anything that is polar has this force. It's our medium strength, right? Falls in the middle. And if you can get the magnets to get closer together, it gets stronger. Okay? All right, London is our temporary dipole because it's uneven. That's what that word right there says. Okay? Now, what causes this temporary dipole? What's causing it to happen? What's going to the side, Logan? The electrons, right? It's just the electrons moving. So, every single atom and molecule on Earth experiences this force because the only requirement is it needs electrons. So everything experiences this to some extent. That's why it's also the weakest. But the bigger molecule you have, aka meaning more electrons, the stronger the force can become. So molecules with a ton of electrons can have quite strong London forces because they have so many to shift. And then our last one, there's our hydrogen bonding. So once again, we're looking for N, O, or F directly bonded to H. Once again, keyword, you have to have a direct bond with the H. It's the strongest of all three forces, but it's still not as strong as a real bond. So you have to have N to H, O to H, or F to H to make this bond happen. Okay, everyone good there? Okay, on the table below, we're going to do the first three examples together, and then you'll try the last three for some smiley faces, okay? So this is what your homework is going to practice, and this is pretty much what ICANN 8.4 is being able to do. Okay, so given a structure, can you tell me what forces it has? So let's start with London. In the table up above, what type of structures have London forces?
All
So
of
this should be an easy point. Yes, yes, yes. Everything has London. If you missed that on the test, I don't know how to help you anymore. Yeah.
Why did they call it London anyway?
It was actually named after the guy who discovered it. Yeah, his last name was London. So, yeah, kind of weird. Okay, looking up at the table above, what type of molecules have dipole forces? Polar. So to know if something has a dipole, you gotta look at it and see if it's polar to begin with. So, is this molecule right here polar? Yes. So since it's polar, maybe make a note of that. Yes, it has dipole forces. Those are always linked. Polar means dipole forces. If it has dipole forces, it has to be polar. Okay, this one, polar or nonpolar? Good. Not polar, so it does not have that force. Polar, nonpolar?
polar.
Good, so this is polar, so yes. Questions on identifying dipole-dipole force? All right, hydrogen bond. First off, you gotta have hydrogen somewhere. So that one, no. What's the next requirement though with hydrogen bonding?
No.
N, O, or F. So this one, nope. But it's not just that it has N, O, F, and H. It has to be a direct bond. So in this structure, we have an F, we have an H, but they're not bonded. So this would still not be hydrogen bonding. Questions? Okay, try the next three with your table, buddy. Ready, set, go. So fill in the rest of the table, and then we'll check it. You can set your pencils down just when you're done so I know you're ready to check it. And I did checks and X's just so you won't confuse yourself later and maybe like be like, why did I, is that blank for a reason? But however you want to designate it, it's there or not. So that's our homework.
Which one? What's our homework again? Sorry.
The next, it looks pretty much, well, kind of like that chart, but it's the next paper in your packet, behind the lab. Yeah,
Okay. And this is what we're doing here today.
pretty much. Yeah.
This is the last part of the unit.
Yep, so we'll cover that.
And then there's a review day and then the quiz.
Well, so next time's a combination of that last page and review, because it won't take very long. It's kind of like we're just going to talk about the application of these properties. So.
All right.
Okay, really quick, before you all jump into your homework, let's check this just to make sure we don't do anything. Hopefully we can fix any misunderstandings we have now, okay? All right, you can have a smiley face for every... Well, I guess last period I gave it for every box. So I guess I better do the same too, huh? Okay, so for every box, if there's a check and you got a check, then you get a smiley face, right? Okay, so that should be 3 easy smiley faces for that. London, and answer is always yes. Okay? For dipole-dipole, this does not have it. This one does not have it, but this one would. Questions on that? And this one would not have hydrogen bonding. This one would have hydrogen bonding. And this one would as well. Questions on any of those? 9, actually. It's which I said for every box. Yep, even the London ones, even those are like default. So, no questions for now? Okay, so your homework assignment is the next one in your assignment packet. It looks like this, and there's actually 2 copies of it for fun. So it wasn't meant to happen, but because of it, here's what we're going to do. Because the front side is all we're doing today. So we'll do that today and then turn it in, and then next time we'll do the back side of the second page. And then put it back in.